Hi, I'm David Bonzak, Product Manager for Rheology at TA Instruments. I'd like to welcome you and thank you for joining us for today's webinar. If you get disconnected at any time, please use the instructions you received to log back in. You can access various content by clicking the Documents widget at the bottom right-hand corner of the screen. This includes speaker bios and additional file downloads. If you need help at any time, click the question mark widget. Please ask any questions you may have at any time during the presentation by submitting them through the Q&A window. We will answer as many of these as possible at the end of the webinar. Our presenter today is Neil Cunningham, the founder and director of the Center for Industrial Rheology. Neil started his career in rheology in 1995 as a sales engineer for TA Instruments and Rheometrics Scientific. Since becoming an independent consultant in 1998, Neil has consulted for hundreds of companies worldwide and has trained an estimated 3,000 formulators, researchers, process designers, and quality controllers in the principles and practical application of rheology and viscosity testing. In 2012, Neil founded the Center for Industrial Rheology, a specialist laboratory in Hampshire, England, providing sample testing services, practical training courses, and advice for companies looking to gain a better understanding of the behavior of their products. He has gained a reputation for having an accessible, enthusiastic approach to rheology, and for his ability to convey important, but sometimes intimidating technical concepts to even the most non-technically inclined person. The title of Neil's talk is Essential Tools for the New Rheologist. Neil?
Thanks, Dave. Hi, I run the Center for Industrial Rheology. We provide testing services, practical training courses, and advice for companies that need to get a better understanding of how their products flow. So typically, our customers are manufacturers of consumer healthcare products, pharmaceuticals, foods, some industrial products, so coatings, inks, paints, adhesives. And often what they're looking to do is to gain an understanding either from a formulation point of view on what are the impact of changes in the constituents in the material, or maybe they're looking to benchmark their products against competitor product and see how the product relates for texture, application properties, skin feel if it's a topical product, or mouth feel if it's a food. And so there's a whole range of different applications for rheological testing. Typically, when they come to us, up until that point, they've just been using some simple viscometers, much like this Brookfield type instrument here. So these are simple, they're easy to use, they're low cost, and they're everywhere. You can find them in all labs. And the way these instruments work is that you select a spindle and a speed, and you immerse the spindle into the sample and start the instrument running, and you'll take a viscosity value off the screen. So this is what we call a single point test. So a single point test is typically the way that these instruments are used. And single point tests are great for quality control managers. So they love just a single number for viscosity. So usually a quality control manager has a sheet, a QC release sheet that's got maybe pH and appearance, density, odor, and they only have a single place on that sheet where they can input a number for the viscosity, typically in centipoise. Okay, but anybody getting into rheology will then realize that just as it's impossible to describe a banana by its color alone, it's impossible to capture the complex rheological attributes and properties of the sort of materials that we're dealing with just a single number. And there's a more fundamental issue than that as well, and that is that, and I think there's a really great quote actually from Abraham Maslow, that if all you have is a hammer, everything starts to look like a nail. And you can apply this to the use of viscometers, because if all you have is an instrument for measuring viscosity, a liquid-like characteristic, then you start to think about everything as a liquid. And as we'll see, that's actually far from the case. So we need to learn a little bit about rheology, and what I'd like to do is show you a few basic tools and techniques. I like to think that learning rheology is a lot like learning to play a musical instrument. The fundamentals and the theory are absolutely essential if you want to become a virtuoso. But equally, just like the kid who gets his first electric guitar, there's nothing wrong with learning a few classic riffs and power chords, cranking up the volume and knocking out some rock classics. And that's really what I'd like to do today, is to teach you some of Rheology's classic riffs really and power chords. And what these will do is they will enable you to, if you have a rheometer, to get started, taking some measurements and get some value out of your instrument. And if you don't have a rheometer, but you're the recipient of data, maybe from a lab like ours, then you're going to get a better understanding of how to read the music, so to speak, really. Okay, so just to cover some fundamentals here, rheology is defined as the study of the flow and deformation of matter. So flow is a liquid-like characteristic. We often think about rheology as being the study of the flow of fluids, but the deformation aspects are absolutely crucial, and understanding of those deformation aspects are crucial. So what we have here on this slide is we've got a syrup on the left-hand side, something we can consider as a fairly good example of a liquid, and then we've got a gel on the right-hand side, something that's a pretty good example of a solid. And when we say a solid, what we mean by that is a material that will exhibit an elastic bounce back. So it exhibits some bounce back ability, some elastic deformation, storage of energy, and then when you remove any applied stress, the material bounces back to its original shape. So this is great. Here we've got a good example of a liquid and a good example of a solid. But when you get into the real world of manufactured products, then things are a lot more complex. And what we have here are a whole range of materials that exhibit a combination of solid-like characteristics under some circumstances and liquid-like characteristics under others. So how do we deal with these? Well, what I'd like to do is to show you a simple categorization, a simple method for categorizing these products that will assist you in making some decisions as to what are the best metrics to capture for these materials, and what are subsequently the best rheological test methods to perform on these materials. Okay, so the categorization basically looks at the overall rheological traits of the material. So we can divide these up into two categories. We have materials that exhibit structured liquid behavior and materials that exhibit viscoelastic behavior. So structured liquid behavior is typical of, for example, the ketchup and the mayonnaise there. These are materials that have a soft, solid structure when they're at rest. And when you apply sufficient stress to exceed what we call the yield stress, then we get some flow occurring. And so we'll get some liquid-like behavior once you exceed that yield stress. Often it's only very brief, and as soon as the stress is removed, the material undergoes what we call a thixotropic recovery back to its original soft, solid structured condition. Viscoelastic materials, on the other hand, these are materials that will exhibit some, well, they look like liquids. They spend most of their time looking like liquids, but you can actually get them to elicit some elastic properties, some bounce back abilities, some elasticity under certain circumstances. And typically when you try to make them move quickly, they'll start to exhibit this. So what we've got are two groups of materials here, or two categorizations that we can use for making some decisions on how we're going to test a material. And just to summarize then, so structured liquids are soft solids. You apply sufficient stress, you get them to flow. And viscoelastics, they act like liquids generally, they look like liquids, but you can get them to elicit some elastic behavior if you try to make them move maybe too quickly or something like this. Okay, so what we then need is a way of identifying whether our particular material is exhibiting, under any certain circumstances, exhibiting an elastic behavior or a viscous behavior, so a solid-like or a liquid-like behavior. So what we're going to do is we're going to look at what happens when we impose what we call oscillatory shear on a material. So here we have a jello, and what I can do here is I can impose a sinusoidal stress to the jello. And when I do that, what you can see with a jello is that when the stress is zero, there is zero deformation, so zero strain in the jello. And as we reach the maximum stress in one direction, then we see the maximum strain in that direction. We go back to zero, zero strain, maximum in the opposite direction, and maximum strain in that direction. So the strain is in phase with the applied stress. Okay, so that's for an elastic material. Now let's take a liquid. So here we have some honey. And it's a little bit difficult to see here, but if I apply some oscillating stress to the honey, then what we actually see is that the honey flows backwards and forwards. And the position of the honey is not in phase with the applied stress, but it actually lags behind the applied stress. And it lags behind the applied stress by 1/4 of a cycle. Okay, so it can never quite catch up. And when we're talking about a sine wave, we say that a full cycle is 360 degrees. So the 1/4 of a cycle that we're seeing, the lag here, is 90 degrees. So what that does is that gives us a parameter, the phase angle or the phase lag. And the phase lag or the phase angle is a really useful parameter then for identifying whether we have an elastic response in our material, like the jello, or a viscous response, like the honey. So we can tell from this the phase angle. If we have a 0 degree phase angle, then we have an ideal elastic solid. 90 degree phase angle, we have an ideal viscous liquid. And it's a really powerful tool for us. And so the combination of the ability with a high-end rheometer to be able to apply some very gentle stresses to probe our material, to gently apply some stress and remove the stress, and an oscillatory mode of operation. So to push and then let go and push and let go. So that combination of those two characteristics are a really powerful combination that gives us a lot of characterization capability in an instrument. Right, okay, so what I'd like to do now is show you some techniques that we can use for obtaining some simple rheological snapshots of, firstly, structured liquids, and then secondly, viscoelastic materials. So what we can see on this slide is an example of what we call an oscillation stress sweep. In my lab, this is possibly the single most commonly run test on the materials that we get in. And this test has been performed on the yogurt that you can see there. Now, if you look at the yogurt, there's some strawberries sitting on there. They're not floating on there, but they're being supported by the structure in the yogurt. And we can use phase angle as a structure detector and for monitoring and identifying and understanding that structure. And so what we're doing with the oscillation stress sweep is, just as we did with the jello, we're applying some small stresses, but we're actually then ramping up those stresses, so we're getting to larger and larger stresses, and this is all done in rotation on the rheometer, obviously. And you can see with the yogurt that we're getting a low phase angle in the first part of the test. So as we're applying those low stresses, starting off at 0.1 pascal, it's a very delicate stress, and then gently incrementing the stress there. And we're seeing a low phase angle, which tells us that we have what we call an elastic dominant behavior. So the yogurt, under those circumstances, in the low stress situation, is acting more like a solid than a liquid. And I've actually got a pudding here, a tapioca pudding, and we can see the same thing here. I can give it a little wobble, and that is an indication that we have this elastic response. Okay, but then as we ramp up the stress, what you can see with the yogurt is that eventually the phase angle goes from a low value and starts to rise. And then once we get up to around about 60, 70 pascals, then the phase angle shoots up towards 90 degrees. And what's happening here is that the yogurt is going through a yield. It's going through the yielding behavior. And so we're applying sufficient stress to disrupt the elastic structure in the yogurt and turn it from being a soft solid into essentially a liquid. And we can see the same thing with the tapioca. So small stresses, we get largely an in-phase behavior, the oscillate, the bounce and the wobble here. But if we ramp up the stresses, then what we can see is we start to see the tapioca shearing, and we're getting this kind of avalanching. And what's happening here is we're applying sufficient stress to disrupt the structure in there. And so everything starts to go out of phase. Okay, So that's for the yogurt. We can compare the yogurt to, here we have a smoothie. And what you can see with the smoothie is the same behaviour. We have that elastic dominant behaviour, so the soft solid dominant behaviour at low stresses, but it yields at a much lower range of stresses. Okay, and that's ideal for a smoothie, because a smoothie, you want to be able to pour the product, and you don't want it to feel too thick when you're swallowing it. Okay, but the really interesting one here is the fruit juice. So here we have a great example of the ability to identify a soft solid structure in a fruit juice. And so what we've done here is we've taken an orange juice and we've performed the oscillation stress sweep on this. And you can see, just as with the smoothie and the yogurt, you can see that soft solid structure, that plateau in the phase angle at low stresses. Incredibly low stresses, very gentle stresses there, but nonetheless there is a soft solid structure there. I think this is a really great consciousness raiser, because what this does is it illustrates the concept that in something that we would always think about as being a liquid, fruit juice, we've actually got a soft solid structure when it's at rest. So you think about it, when you look at these cartons of fruit juice on the shelves in the supermarket, they're at rest, they've had time to assemble this soft solid structure, and so they're better off described as a solid than a liquid under those conditions, albeit an incredibly delicate one. I've got another really good example, actually, of this sort of behaviour. I was in a Japanese restaurant recently, and I was served up a bowl of miso soup. The miso soup shows a really great combination of the buoyancy of the particles that are suspended in there and the interactivity in them. And this particular bowl of soup, it was showing some really great behaviour, so I had to actually film it. Okay, so here's a bowl of soup. What I've done is I've just given it a stir, so I've dispersed all the particles in there. And what you can actually see in there then are, the first thing that appears are you see these dark lines appearing. Now these dark lines are actually the boundaries between convection cells, where plumes of meso particles are coming up to the surface, then dropping down at the sides. So we're looking from above here. And this is essentially the same process as goes on in the Earth's mantle, in the Earth's crust, when we get tectonic plate formation. So these are the fault lines between the tectonic plates of meso. But then what happens is, very quickly, everything stops moving and we get this coarse, sort of fluffy appearance. And what's happened here is that the particles have associated together. There's been a colloidal interaction. The particles have associated together, and they've generated, essentially, a really soft, solid structure. And it's a structure that we could ultimately measure on the rheometer. And although it's an incredibly delicate structure, it's sufficiently strong to overcome the convection forces that we saw in the soup there, and also to overcome the inertia and the momentum that I'd put in from stirring the soup. Okay, so this is a really great example, I think. Again, another consciousness raiser that illustrates the concept that we have this incredibly delicate soft solid structure in a lot of materials. And it's a structure that we mustn't ignore, because that structure will impart a lot of the desirable attributes to a material. So just to summarise, in the soup we had that what I call it the tectonic stage, where we have these convection cells. They're called Rayleigh-Bénard cells, rising up and then dropping down at the sides. But then very quickly we reach the soft solid stage, where this structure had assembled itself. Now just bear in mind that if you were to measure this with a viscometer, the viscometer is just going to drive its way through that structure and will disrupt that structure before it even starts taking a measurement. So really, viscometers look pretty delicate, but in rheological terms, they're a bit like taking a sledgehammer to the structure. And so that ability that I talked about earlier, the ability to be incredibly delicate with a material, that ability that you get with a research rheometer, and also the ability to push and let go and push and let go with an oscillatory testing mode, is a very powerful tool there. Okay, so what else can we get from oscillation? In addition to the phase angle, which gives us this measure of the relative dominance of elastic or viscous behaviour, and from that we can get yield behaviour. The other bit of information we can get from there is, one of the other bits of information, there's a load we can get from these tests, but the complex modulus. The complex modulus is a really useful parameter. What it is essentially is just the resistance to deformation, the overall resistance, the stiffness or the rigidity of that soft solid structure. A lot of the companies that I'm dealing with are producing, for example, creams and ointments and lotions like this. And the complex modulus is one of the characteristics that will determine the appearance and some of the textural attributes. Okay. In fact, what I've got on there then is a slide that shows an oscillation stress sweep test performed on an ointment, a cream, and a lotion. You can see the ointment, the red curve there, has a very high complex modulus plateau. So this means that the ointment is very rigid, very stiff, below the yield. But then as we ramp up the stress, we soon reach the yield, and you can see as we disrupt that elastic structure, we see a significant drop-off in the rigidity. And it's a huge drop-off, actually. It's dropping off in factors of 10 there. Okay, that high yield is necessary in an ointment because typically what you want in that product is something that will resist being washed off when there's water running over it, for example. Okay, a cream. So here I've got a cream, a tub of cream. The cream you can see has complex modulus plateau value, so the rigidity in the middle there, and also the yield stress in the middle. And with a cream we want something that's got a bit of body to it. If we compare that to the lotion, okay, so here's a lotion here, and with a lotion, it's important that we can pour a lotion out from the bottle. So, and it's that pourability is a function of the yield stress of the lotion. So it's the low yield stress that gives us the ability to pour the material out of the container. And evacuation containers is a very important thing in a lot of manufacturers of consumer goods. And yield stress is often the determining factor for those products. One thing is very important not to confuse rigidity, so the complex modulus plateau, with the strength of the structure. And I've got a good example here. Okay, what we can see here is an example of two hair gels. And the hair gel, the number one there, the red curve, we're seeing a low complex modulus plateau for that. So it's a soft gel. It would be wobbly in the tub. You can see it bounce, okay, but it's got a high strength. Okay, it's got quite a high yield stress. If we compare that to hair gel number 2, the green curve, that's got a high rigidity and a lower strength. Okay, so it's important to just appreciate these two concepts, that rigidity, the stiffness and softness, or the strength, whether it's strong or weak, are two separate things. And just really to summarize that, I've got a little map here that's got modulus on the y-axis, yield stress on the x-axis. And what you can see, the whipped cream up in the top left, so whipped cream has a stiff, rigid structure, but it's very delicate. You only got to lay a spoon on it or something, and that structure will break. If we compare that to the Jello in the bottom right, Jello is soft and wobbly, so it has a low modulus, but it's strong, so it can support a fair bit of weight. We compare it to the chili dipping sauce, the bottom left, that's both soft and weak. So if you have a bowl of chili dipping sauce, you can see it wobble. But you can also pour it as well, so it's got a low yield stress. And then you look at the rather menacing looking gummy bears there. So they've got a combination of rigidity, the high rigidity, and a high strength, a high yield stress to them. Okay, so what we've done so far is, in our snapshot of the rheology of structured liquids, is we've looked at the structural aspects. Once we go beyond the yield point, then we're going to get into flow behaviour. And there are a couple of ways that we can assess flow behaviour. We can use two different approaches for viscosity profiling over a range of shear rates. We can perform shear rate controlled sweeps and shear stress controlled sweeps. And they've both got their own particular advantages and disadvantages. One way to think about these is that shear rate sweeps are really good if you're trying to characterize a forced flow situation. If you have a situation where machinery is driving a flow process, then we can kind of recreate that situation on a rheometer by identifying the range of shear rates that are evident there and applying those and looking at the viscosity profiles across the range. And what you can see there are three coating formulations showing shear thinning behaviour and leading out into a what we call an infinite shear plateau, a high shear plateau behaviour. If we contrast the shear rate sweep to the shear stress sweeps are generally far more delicate tests, and typically what we're doing there is we're probing the structure of the material and then looking at what happens as we get that structure to disrupt and then the product goes into a flow behaviour. Shear stress sweeps are great for characterising what I call free flows, so flows that are driven by gravity or capillary forces, but typically in fairly gentle situations. Really good example actually of thinking about both is imagine if you're painting a wall. So when you're applying the paint, you're in a forced flow situation. You're in charge of the paint. You can make it flow at the speed that you want it to flow at. As soon as you stop painting, you remove the brush, then gravity and surface tension capillary forces take over, and now you're into a free flow situation. Now the paint is in charge. The paint's rheology determines how quickly it's going to flow. And so we can use this combination of shear rate sweep viscosity profiles and shear stress sweep viscosity profiles for characterizing those two separate situations. Okay, so we've analyzed the structure, we've analyzed the flow behavior, but those transitions from soft solid structured material to a liquid-like flow behavior and back again, they don't happen instantaneously, but they take time to occur. And this is where thixotropy comes in. So really good example to think about this is back in the time when ketchup was sold in glass bottles, and you had two strategies for getting the ketchup out of the bottle. You could either take the lid off, tip it up, and give the back of the bottle, the base of the bottle, a whack. And what you're doing there is you're applying enough stress to overcome the yield stress of the ketchup, and then you would get a slug of fairly structured ketchup coming out onto the plate. The other approach is you leave the top on, you give it a really good shake, and you know intuitively that you've got enough time to remove the top and to tip the product out, and the product will still be at a sufficiently low viscosity to get the product out. So in actual fact, it's the yield stress is probably the key characteristic there. What you've done is you've shaken up the ketchup, you've disrupted that structure, and because of the significant thixotropic behavior in ketchup, so a slowness in recovery, then that gives us time to get the ketchup out of the bottle. Were it the case that shower gel were ever sold in glass bottles, would be in real trouble, because there again you have an equally shear thinning material, an equally non-Newtonian material as ketchup. The difference with shower gel is that if you shake it up, you'll affect a viscosity decrease, but only momentarily. And the moment you stop shaking, it's going to snap back to its original viscosity value, and you'd never have time to get the lid off and pour the stuff out. Okay, so it's good to think about thixotropy as a slowness. It's slowness in achieving an equilibrium, a stable equilibrium value following changes in the applied shear conditions. One of the test methods that we can use on the rheometer for assessing thixotropy is three-step tests. So a three-step test typically involves applying a gentle shear or gentle oscillation as a conditioning step, and then applying a large shear or large amplitude oscillation as a breakdown step, and then going back again to the gentle conditions to look at the recovery. And we can see that in the two results here. We have a topical cream on the left-hand side, and this topical cream is showing the phase angle starts off fairly low, around about 30 degrees in the conditioning step. We apply some high strain oscillation to that, and the phase angle rises up to 70 degrees, so we've disrupted structure. And then when we remove the applied, or we reduce the applied deformations, then we get a pretty rapid recovery back to that low phase angle, highly structured condition. If we compare that to the toothpaste, so here we see the toothpaste, when we apply the high deformation, the large strain oscillations, then again we get the phase angle rises up to a higher value. That tells us that we've gone from an elastic dominant product to a viscous dominant product. But then when we return back down to the gentle oscillations, we can see that the toothpaste is undergoing a much slower recovery back there. And so we say that toothpaste is highly thixotropic and the cream there is less thixotropic. Okay. So these are the approaches, some simple approaches that we can take for assessing structured liquids. We can perform the oscillation stress sweep test for analysing the strength and rigidity of the structure, viscosity shear rate and viscosity shear stress profiling for understanding the flow behaviour, and then thixotropy tests for getting an understanding of the time scale, the temporal aspects of those changes between those two conditions. Okay, so what can we use then for obtaining snapshots of viscoelastic rheological behaviour? Okay, well, I'd like to show you another example here that I think is pretty interesting. What we've got here is a shower gel. If I tip up the shower gel like this and I move it slowly, then we can see that it's flowing backwards and forwards. So it's just acting like a typical liquid there. And in fact, if I compare it to this corn syrup here, there's very little difference under these conditions. So they're showing kind of similar viscosities, really. But if I then take the shower gel and I give it a bit of a shake, or I tap it, what we can see there is we can see some clear elastic behaviour. We're starting to see some elastic properties showing themselves. And we don't see that with the corn syrup. If I give that a shake, it barely moves at all. Okay, so we're getting an elastic wobble in the shower gel that we don't see in the corn syrup. The reason for that, corn syrup is a pretty good example of a fairly basic viscous liquid. The shower gel is a really good example of a viscoelastic material, and specifically displaying a timescale dependent viscoelastic response. So what we can use is we can use oscillation frequency sweep testing to analyze that timescale dependent response better. So what we can see on this slide is in the top left-hand corner, we've got oscillation frequency sweep results performed on 2 hyaluronic acid formulations. So hyaluronic acid is a biopolymer. It's known for its stringiness and sliminess and slipperiness, but it can also be cross-linked for various applications. And what you can see there is that the graph, the plot showing the cross-linked hyaluronic acid, we see the phase angle is low over that range of frequencies. And so if you can think about it, starting from a high frequency and coming down, then we have the phase angle remains low over that entire range of frequencies. So that's telling us that we're seeing an elastic dominant behavior across that entire range. If we compare that to the non-cross-linked HA, now this is just a high concentration solution. And the non-cross-linked HA is a lot more like the shower gel, in that we're seeing at high frequency deformations where the time scale of deformation is short, we're seeing an elastic response. But at long, slow frequencies, long time scale deformations, we're seeing a viscous response, a liquid-like response. So the phase angle at high frequencies is low, but as we go down in frequency, the phase angle rises up. So the liquid relaxes, or the material relaxes into a liquid-like behavior. You can often see this with shower gel, actually. When you squirt a dollop of shower gel into your hand, the moment it hits your hand, you can see that elastic response. You can see that sort of elastic bounce, and very quickly it then relaxes into this liquid-like behavior. Okay. There are other ways of, there are a whole range of other rheological viscoelastic metrics that we can obtain, and other ways of representing the same data here. And what you can see in the bottom left is we have we've pulled out there the storage and loss moduli. Okay, so the storage and loss modulus are 2 individual moduli that can be resolved out if we know the complex modulus, the overall rigidity of the material, and the phase angle. And you can see in the little vector diagram on the bottom on the bottom right there, we see the storage, or the elastic modulus is often called, and the viscous modulus, G prime and G double prime. And again, what we can see is for the cross-linked HA, we see that the storage modulus, the red line, remains above the viscous modulus for that entire range of frequencies. Whereas for the non-cross-link, so the solution, we're seeing a classic viscoelastic crossover behavior there. We see at high frequencies, the storage modulus is higher than the viscous modulus. As we go down in frequency, then we see a crossover into viscous dominant behavior, so liquid-like behavior at low frequencies. Okay, something else that we see with viscoelastic liquids is when we expose them to continuous shearing. Well, there's two things that we can get from this. So firstly, we can get a viscosity shear rate profile. And typically what we'll see with a viscoelastic liquid, for example, a polymer solution or a surfactant-based product like the shower gel, is we will see a clear zero shear viscosity plateau and then going into a shear thinning region. That slide on the top left there, I'm really pleased with this slide actually. What we've done here is we've looked at a range of eye drop formulations. These are formulations for dry eye conditions. And I think it's quite incredible the range of viscosities that we're seeing there for material that anybody would think of as just being like water, really. And we have 4 formulations there. We've got an old low-cost formulation that's been around on the market for a long time. That's the red line. The green line is a premium product that's been around for a while now, and it's a current premium product. And then the other 2 are part of the kind of the new breed of sort of super lubricants that are coming through these days, and using various polymers like HA and CMC, carboxymethylcellulose, and various things. Typically, with an eye drop for dry eyes, what you're looking for is a material that will have a high zero shear viscosity. So this will mean that between blinks on the surface of the eye, the high viscosity will maintain a good residence time for the liquid, so the liquid won't drain away. Okay. But when you blink, you don't want that high viscosity because it's going to feel like you've got syrup in your eyes or something like that. So when you blink, you want the material to shear down to a much lower viscosity. So blink shear rates of various values have been reported, but typically anywhere between sort of 4,000 and 28,000, I think, reciprocal seconds of shear rate have been reported for that. And what we can see there is that certainly the purple line there, the super lubricant B as I've labelled it, we can see that has a combination of a high zero shear viscosity and then it shears down to a low high shear viscosity. This is the ideal behaviour for one of these formulations. Okay, so that's viscosity profiling of viscoelastic liquids. But the other thing we can do is we can look at what we call the generation of normal stresses. So normal stresses are stresses that are generated when a viscoelastic liquid is sheared, and they are normal, so they're perpendicular to the plane of shearing, so perpendicular to the direction of shearing. You often know when you have a material that generates a lot of normal stress because I've got some rather strange hair gel here that goes under the name of gorilla snot, and what you can see, this will exhibit normal stresses, and what those normal stresses do is they will lead to an extrudate swell effect. As I squeeze the material out of the nozzle, it swells to a higher diameter than the nozzle. Delightful material. And that extrudate swell is the manifestation of the stresses that are built up in the material as they come out into the open world, and then they're relaxing and the material is expanding to a larger diameter. Materials that exhibit this normal stress generation are typically often very difficult to process. They can cause some difficulties, and if you're trying to get material through nozzles or pumping and filling and those sort of processes, you're trying to make the material move quickly, then it's the onset of elastic behavior and the growth and the generation of these normal stresses can be quite problematic. And we can actually measure those normal stresses on the rheometer. So what you can see on the bottom right-hand side there, these are four starch dispersions that have been gelatinized and then exposed to a shear rate sweep. And you can see for the dent maze and the waxy maze viscosity profiles, also normal stress profiles, the stresses remain pretty low throughout. But the tapioca and specifically the potato starch, that's showing a huge normal stress generation as we increase the shear rate there. And that potato starch is typical of the sort of material that would exhibit that sort of behaviour. It's stringy, it's slimy, it's snotty, it's gooey. It's got very good film forming characteristics, and it can be a good lubricating characteristics as well. So those are typical kind of hallmarks of a highly viscoelastic material. Okay, so we have the oscillation frequency sweep that we can use for characterizing the onset of elastic behavior with decreasing timescale, and then we have viscosity profiling and normal stress profiling that can illustrate the behavior under higher shear for viscoelastic materials. And so these are the methods that we can use for snapshotting our viscoelastic products as well. Okay, so just to summarize then, what we've looked at here are two methods, two approaches. First of all, we've got this categorization approach where we can take the materials that we're dealing with and we can divide those materials up into structured liquids and viscoelastic materials. And this helps us then choose the metrics and the test methods that we're going to use for characterizing them. And for structured liquids then, we can look at the rigidity of the structure, we can look at the strength of the structure, we can look at the viscosity under shear, and we can look at the temporal aspects, how long it takes to shear down, how long it takes for the material's viscosity and yield stress and structure to recover again when we stop shearing. And then for viscoelastic materials, the most relevant characteristics there, viscosity under shear, the onset of elasticity, or really what we're talking about there is what is dominant at relevant timescales, elastic behavior or viscous behavior. And then what we can also do is we can look at the growth in normal stresses. And we can identify materials that are likely to generate lots of normal stresses, and that's likely to correlate with difficulties in processing, but also some handling characteristics and film forming, stringing and sliminess and those sort of things. Okay, so just to sum up, just remember that rheology, really what we're doing with rheology is we're mimicking what we do when we handle materials. So whenever we take a material and we want to get a feeling for what it's like, we look at it, we give it a shake, we give it a bounce, we'll spread it and smear it and all these kind of things. And what we're doing with the rheometer is we're doing exactly that. We're just doing it in a much more controlled manner. So just remember the rheometer is a tactile sort of sensual instrument, and we're using it to feel our materials. So think about whatever you would do to a material when you're assessing it physically, manually, and then you can recreate that on the rheometer. Okay, hope that's been useful. Thank you very much.
Thank you, Neil, for that very interesting presentation. A recorded version of the webinar will be archived and available through the TA Instruments website. We'll now begin the question and answer segment of the webinar. If you haven't already, please submit your questions to the Q&A window. We'll do our best to answer as many as possible.
All right, Neil, our questions are coming in, and our first question, or I should say a general theme that we're seeing from several questions, is on the difference between controlled stress and controlled deformation or controlled rate or controlled strain. Can you speak to some of the differences, both in operation as well as the meaning of the data, between controlled stress and controlled strain or strain rate, both in oscillation as well as in flow testing?
Okay, thank you, Dave. Okay, so I think from a practical point of view, it's worth thinking about the main differences between controlled stress and controlled rate or controlled strain testing. So I think, first of all, it's useful to bear in mind that controlled stress testing is a very gentle approach, and it tends to be a lot more gentle than controlled strain and controlled shear rate or strain rate testing. So controlled stress testing, you're applying some very gentle, you're just gently pushing the sample and you're looking at how it responds in various ways to that applied stress. Controlled strain testing or controlled strain rate testing, obviously you're making the sample move to an either certain deformation or move at a certain rate. And we're seeing the sort of stresses that are required to affect that kind of change. I think it's probably useful to think about relating that to real life flow situations, in that you do have these free flows where the driving force behind, or the driving movement behind the flow, is either a capillary, surface tension, or gravity. And there, controlled stress is a much more relevant way of mimicking that sort of situation. And then you've got other situations where you're making a material flow at a certain rate. So you're pushing it, you're making it flow at a certain rate, and so a controlled rate test would be a more practical method there, a more relevant method there. From the point of view of practicality, it's often the case that a simple shear rate sweep tends to be a lot quicker at getting a quick feel of a material rather than performing a test in the controlled stress mode. The behaviour of a structured liquid in a controlled stress mode can be a little bit more unpredictable, and so it takes a little bit more trial and error to arrive at the correct range of stresses to apply. So we can often have really a quick feel, as I said in the video, a quick feel of the material, and use a controlled rate mode there, really, just to understand that first of all. And then we can probe a little bit deeper with a controlled stress test. The other thing about controlled stress test, though, is because it tends to be a more gentle test, then we can probe down at very low shear rates and very low shear conditions. Rheometers, although controlled rate capability and controlled stress rheometers is now really excellent with the current algorithms and processing, controlled stress testing is still their natural mode of operation. And so if you really want to get down to very low shear rates and measure what's going on, then controlled stress tests can be more useful there. Thanks, Dave. Hopefully that answers the question.
Okay. Yeah, great. I think that was a great answer, and shared a lot of insight. So one specific question, and I think a question that I often hear from people trying to understand the right experimental protocol to solve the answer they're interested in, is about the yield stress. And there are several methods that may be sort of bandied about in the community as to how you might measure the yield stress, but can you give any recommendation or insight into the different methods, or specifically, is there one sort of best method for measuring the yield stress of a material?
Okay, thanks, Dave. Yeah, that's a really good question. There are, anybody getting into rheology, you soon learn that there are many different ways of obtaining a yield stress value for a material. I think the first thing to realize is that yield stress, the term yield stress, tends to make you think of it as a single number, a single event that occurs. But in actual fact, as you'll see, as you start to ramp up the stress on a material, the yield process kicks off at some fairly low stresses and then can extend through a whole range of stresses. So it's more accurate, really, to talk about the range of stresses at which yielding occurs over, rather than a single yield stress. However, for practical purposes, a single value is useful because we can then use that for comparing materials and benchmarking and that sort of thing. So that said, I like an easy life, and I found that the oscillation stress sweep test is the fastest, simplest, and often the most repeatable method at getting a quick understanding of the yield stress, or the range of stresses over which a material yields. It tends to be a lot more repeatable, and it's very easy to perform an oscillation stress sweep. You can often work your way through a range of stresses over just a few minutes and see a very clear indication from the rise in phase angle from a low value to a high value as to when that yielding is occurring. And then for a simple quantification, there are various ways of identifying a yield stress value from that. At its simplest, you could take the point where the phase angle crosses 45 degrees as an indication of where the material has gone from a more solid than liquid, elastic dominant material to a more liquid and solid viscous dominant material. The other ways of performing yield stress measurements, well, there's a whole range of ways. The more traditional methods before the advent of controlled stress rheometers would involve applying a range of shear rates and then obtaining what we call a dynamic yield stress, where you're modeling the flow curve and using an equation to extrapolate back to a zero shear rate for obtaining a yield stress from there. And that can certainly be useful in some situations. It's a nice quick test, but as I say, the test method that I use and we tend to use the majority of the time in the lab here is the oscillatory stress sweep test, which is an up ramp, gives us a static yield stress, measures the point at which the material gets moving. And I think certainly if I was to choose a single test, that would be the single most commonly performed method that we would use. Thanks, Dave.
Okay, great. We've had a few questions about thixotropy, and so maybe to combine a couple of those questions. One is it possible to measure thixotropy in a rotational experiment, so a sort of a steady flow or a flow experiment? And then to a more applied question, specifically about one of the materials you talked about, yogurt, would a high hysteresis area be considered to be a good structure or a weak structure?
Okay, thanks, Dave. Okay, from a practical point of view, there are various different methods of measuring thixotropy. The old traditional type, which is performing an upsweep followed by a downsweep, I prefer, actually, I tend to stay away from that, and I prefer to run three-step methods. So three-step method involves a period of either small deformation, small stress, or low shear rate, and then ramping up to a high deformation, or stepping up, I should say, to high deformation, high stress, or high shear rate test, and then holding that for a period of time to destroy sample structure, and then dropping down again to the gentle regime, the small shear rate, or small strain, or small stress. With that method, the good thing about that method is that within each individual step, you've only got one variable, and the only variable then is time. So when you're performing an up-down sweep, whether it's in a controlled shear stress or controlled shear rate mode, you're changing the shear rate or the shear stress, but you're also changing the time that that shear has been applied for. And that can make things a little bit tricky down the line if you're getting some results that you're trying to deconvolute, and you're trying to separate out the effects of time and the effects of the intensity of the applied shear. When it comes to the three-step methods, there are three approaches that I tend to take in the lab here, and that could be either a stepped shear rate, so we start from a low shear rate, step up to a high shear and back down to a low shear again, and look at changes in the viscosity. The other option is we use an oscillatory method, and there we apply a small strain oscillation for a period of time, then step up to a large strain, damage the sample structure, and then drop down again to a small strain and look at the recovery of the structure. And then the other option is to use a mix of those. So we could start off with an oscillatory version where we're applying a small strain, and then for the second destructive step, we apply a lot of shear in one direction only, and then we drop back down again to a small strain oscillation and then look at the recovery. Depending on the nature of the sample, one of the things that can happen is if ever you've got any continuous shearing step in there, so a flow step, so either the first method or the last method I mentioned there, one of the things that can be a bit tricky for you there is that you can end up with some edge failure. So you get a fracture occurring at the edge of the sample, and this is a common experimental artifact in rheological testing with plate and cone plate methods. And if that edge failure persists, then you can get the impression that the sample has undergone an irreversible change. And in actual fact, what's happened is that you've just got a reduced contact area between the sample and the plates there. And so what I tend to find is if we use the little bit more delicate method of using the full oscillatory test, where that middle destructive step and the first and the last step as well, the recovery step, are all in an oscillatory mode, then the strains that we apply in that middle destructive test tend to be insufficient to bring about that artifact, and that could be pretty useful. The downside of that is that we can't apply the same intensity of shear to the sample. So that's some typical ways. There are some other approaches we could take, but we need to tend to take that on a sample by sample basis. Thanks, Dave.
Okay, that's great, and I think a good indication of the things that we can be looking for when we think about thixotropy, and some methods to do that. We have a tremendous number of questions, and we could certainly spend all day addressing some really great and insightful questions here, but in the interest of time, this is going to be our last question, and I think it's an important one and a good one to understand. So for this last question, the attendee asks, for oscillation, it's certainly best if the amplitude is within the linear viscoelastic region. What does that mean, and how do you check for that before you do your subsequent oscillatory measurements?
Okay, thanks very much, Dave. Okay, so yeah, the simplest way to check for that you're getting a linear viscoelastic behavior would be to perform either an oscillatory stress sweep or a strain sweep as an initial test before you go into any further testing, and then to identify, probably the best method there would be to identify the initial onset of any, or initial deviation from any plateau in the elastic modulus, the G prime value. So you can do that, or what we tend to do, it's not quite as accurate, not quite as efficient, but what you can often do is you can look for the first indications of a rise in the phase angle. Obviously, if G prime and G double prime, the elastic and the viscous moduli are dropping at the same point at the same time, that's not going to be picked out from that method. So, so the first method is the more efficient method. Look for the first deviation from G prime, the first drop in the elastic modulus. An alternative, quicker method is to look for a deviation from the phase angle plateau, or even the complex modulus plateau when the sample is initially starting to soften. And then you run these tests, oscillatory stress sweep and oscillatory strain sweep, run those as a precursor to any subsequent testing like oscillatory frequency sweeps or any temperature profiles and or thixotropy tests for that matter. Thanks, Dave. Hope that is useful for you.
Yeah, that's perfect. So thank you, Neil. And this concludes today's program. I'd like to thank Neil once again for joining us today. And I especially would like to thank all of you in our audience for spending some of your day with us today. This webinar, like all TA webinars, will be archived and available through the TA Instruments website. And please look out for future invitations to subsequent TA webinars. And thank you all, and have a great day.